Hello and welcome to another Dave Makes Stuff with nTop tutorial. Today I want to talk a little bit about conformal vector fields and what they are and why they're important in the design work that I do with nTopology. And in the course of doing that, I want to introduce and offer to you to use 4 different custom blocks that I use quite a bit when I'm working with vector fields and doing design work. The first is a custom block for making test shapes, and then 2 custom blocks for making the vector fields, a wavy conformal vector field and a wavy radial vector field. And then I also want to show you a custom block that I use to visualize vector fields. It's a little bit easier to view how vector fields are forming around an object in 3 dimensions. So we will go through all of those in more detail. But first of all, why are vector fields important in my design work and possibly in yours? Whether or not you're doing art or design things, hopefully you'll find something in here that's of use, and you can apply it for your own purposes. So this right here is a simple sphere using the in the lattice section, the stochastic orthoform lattice. So that's one of the most basic uses or reasons to have a good conformal vector field, because the input to the orthoform lattice requires a vector input. And if you want your orthoform lattice to look nice around a surface, then you need to have a conformal vector field. So using that is one reason why it's nice to have to be able to create a conformal vector field. The other one is that I use, and this is the main reason that I have that I developed a lot of resources around conformal vector fields, is for doing growth algorithms. So what you're looking at right here is the outcome of a growth process that started with some seed points at the bottom, and it basically grew. The graph lines grew up the surface of the ovoid and divided and rejoined, diverged, converged together according to a set of rules, but absolutely based around a good well-formed vector field that followed the surface and sort of directed the growth of those lines. So I will. The growth algorithms that I do are that's maybe something I'll look into more in another tutorial. They're quite complicated, but I just wanted to let you know, just to share what what kind of the main one of my main purposes for these is. So let's go back here to the beginning and look at this custom block called test shapes. Now this custom block is nothing special, but I use it all the time, and I just thought I would include it here for you to know about, and then of course to access as well. And I will make these custom blocks available to you. Put the links down below. But what this is just a way to cycle through a bunch of different shapes and surfaces so that I can see how, in this case, how a vector field is responding to the surfaces and things like that. But I use it for all sorts of different things. And this drop down, you can select a sphere, a cube, a point, these cones like this. What's the next one? An ovoid shape, and cylinder and a torus. Now, none of these is particularly difficult to make, but just having them all here together and easy to manipulate is really nice when you're doing sort of iterations and testing things. You can also change the orientation of the different shapes, so you can quite quickly see how test things out. I like to have it in the Z, and let's go back to ovoid here, and actually let's do a sphere. And if you want to, you can also add in some surface roughness quite easily instead of adding another block. And there's all the inputs you would normally find in a surface roughness block: the frequency, amplitude, and the seed value there. So that's kind of the all-purpose custom block that I wanted to show you. Now let's talk a little bit more about vector fields. So let me just introduce you to a basic vector field here first. And this one, let's just open it up. This is just a vector field from a gradient, and the gradient is simply a plane oriented upwards in the positive z direction. So what does this vector field look like? If we visualize it and look at it straight on like that, it's just uh, it's just a straight vertical field. There's no variation in kind of the length of those vectors. It's all just one big unit vector field. You can't really tell from this viewer what direction they're going, but that's what a basic vector field looks like. Now let's open up this wavy conformal vector field here, and let me just introduce you to the inputs here. So in order to apply a conformal vector field, of course, you need a form that you're applying it to. So in this case, we're going to apply it to, let's actually do this with an ovoid that does not have any surface roughness, just to make things easy to visualize. So our input here to the conformal vector field is where we're using the test shape. The tolerance is just, I leave it at 5. It's just the way that the vector field is created, and 5 is good for most sort of real life applications. If you're doing really small detailed work, you might want to, this is sort of a sampling distance, and you might want to put a smaller value in there just so it samples and is more sensitive to smaller changes in the surface. But again, for large things like this, or life standard sizes, that's usually pretty good. The weight factor here. So what this custom block does is it first of all, it applies a conformal vector field around the surface that's mainly going in the z direction, but you can also add some waviness to it. So for our purposes right now, I wanted to just show you a plain vector field. So we're just going to leave that at 0. So there's no randomness being introduced to this vector field at all. And then you have your standard things when you're working with the simplex noise block there, the random seed, and the frequency. So let's just take a look with the field viewer here on what this vector field looks like here. So there we have, I'm going to make this a little bit bigger. This is what I'm talking about when I say a conformal vector field. So you can see the vector lines here are following the surface of the object. And that is the same whether we're looking at ovoids or spheres. You can see that it's following the surface there. Now, if we add a little bit of randomness to it, let's just add 1 degree there. You can see that there's it kind of gets a little bit wiggly, and this is actually easier to see when we look down on it. You can see that things aren't all going straight up. They're of course following the surface of the sphere there, but they're waving around, and that's hard to see. We will see when I show you the visualized vector field here. There's a little bit better way of viewing exactly what's happening within this vector field. Really quickly here, this is less of a conformal vector field, but a radial vector field. So this right here is, again, a wavy radial vector field with no randomness to it. I can apply a little bit of randomness, and you can see that does all sorts of fun little things to the vector field there. So let's just put that back. And we'll close that up here. So before we go further here, I want to show you this way of visualizing vector fields. So this field viewer that's easy to access, of course, it shows you the sort of orientation of the vector field, but doesn't actually show you what direction the vector field is going, and it's also just showing you the vector field in a single plane. Of course, I can move that plane and then take different slices of the vector field, or look at different orientations, but it is a little bit limited when you're working with vector fields and doing design with three-dimensional objects. So this visualized vector field custom block here is really handy, and it lets me look at the whole form and see how that vector field is shaping and moving over top of that form. So let's actually go back here and just make this a straight vector field with no, well, sort of a straight up and down vector field with no randomness to it. And take a look at that. So if you look really close here, you can see that so it's sampling different points. So let me show you this here first. So you've got your inputs to this are the test shape, and then you're inputting the vector field that you're wanting to visualize. The point counts is just how many sample points on the surface of that object that you want to use. And then down here we have line length and the type of line, and whether or not to include normal. So right now we've got this on a centered line. So this is really good for viewing, if you want to evaluate what the tangent is along a particular surface. This is good for visualizing that. Although I usually use the directional line, because most often I'm wanting to get a good idea of when or what direction the vector field is flowing along that surface. And the little normal line there just helps you orient. Of course, that can be turned off if for whatever reason you don't need that. But I usually have it on the direction line with the normal field, and that lets me see what's going on with the vector field around the whole surface. So let's just go in and play around a little bit with this. Let's increase a little bit of randomness to that vector field. And so when we're visualizing it, you can see that it's still mainly going upwards, but there's a little bit of side to side. You can see some little waviness in there. Let's just bump it up maybe to 3 even. So now you can see there's definitely more waviness in there. And again, it's easy to visualize and see how that's acting. If I just look at the field there, it's really hard to get a sense of how first of all, how a stochastic lattice like the orthofoam is going to look on this once I apply that, and more importantly, how the growth algorithms are going to be performed when they're sort of growing up the surface of one of these forms. So that's a good way to do an initial test. Let's start doing some applications to the orthoform lattice here. So the orthofoam block is in your lattice window here, under the stochastic section there. And what it asks for is some points on the surface of your form. So here I've just put some random points on the surface of my test object there, which we're using a sphere. And then that is used to drive these the wavy vector field and the Z vector field, which we're going to use for the demonstration here. And the vector factor is just how much it's the strength of the vector field applying to how the orthofoam lattice is created. So I've set the valency to 2 and the thickness to 4, and let's just take a look at what that looks like. So this right here, you can see I'm using the variable for the wavy conformal vector field, and this is what it looks like. Oh, now I've actually got a lot of randomness in there. So you know what? Let's just turn that randomness off. So you can, and let's just start here, looking at the different using different vector fields within this orthoform lattice. So there's a basic conformal vector field, and the thing that I want to really point out with this, and to kind of help differentiate the importance of these conformal fields versus a normal standard single direction field is if you look at the poles of this, the top and bottom, north and south poles of this sphere. So you can see how they all come together quite nicely, and same at the bottom there as well. And let's just compare that to what happens if we just use a straight Z vector field. So I'm going to put that in there. So you can see on the equator of this sphere, everything is quite oriented because, of course, a straight Z vector field is telling the orthoform lattice to go, predominantly up and down. But you run into trouble around the poles here, because what happens in this area, if I'm just using this straight up and down vector field here, it works around the equator, but the formation of the orthoform lattice are on the top here. Basically, the vector field is just telling it to please move upward, and of course there's no other points upward. There's no other surface upward, so it just kind of gets kind of clustered around there. So that it's not as pretty, and this is what it looks like on a sphere, and you get all sorts of different effects, unwanted effects on different shapes as well. So just to remind you, let's do a comparison. There's the regular Z, and then there's the conformal field on there. So it does look much better. So let's play around with this a little bit. We've got the wavy field on there. Let's just add back in some randomization. So now again, it's nicely forming at the poles of the sphere, but we're getting some kind of wild and crazy variability in there as well. That's just out of curiosity. I don't know what happens if I put it up this high to 10, but okay, so we're getting some pretty wild and crazy directions there. And we could change the frequency of this. Maybe let's soften it up a little bit. Tighten it up a little bit. So there we're getting some tighter curves, and then if we flatten it out a little bit, so all sorts of ways. Boy, I like that little. Those are some neat little growth patterns going up there. So some really neat effects that you can do just by playing around with the randomness of that field. Let's just play around with some of our test shapes here. Let's try out the cones. And let's just bring our vector field back down to something reasonable here. So let's just even do 2. So not a whole lot of randomness, just enough to make it fun. But you can see with this wavy conformal that again, we've got nice convergence around the tip, and the tip down there as well too. And let's just, for comparison here, stick the drive the orthoform lattice with just the straight vector field, and you can see that the straight vector field is basically telling the orthoform lattice to go upwards. There isn't anything up, so it's kind of struggling to find its next point to form the lattice there. So again, compare that to that, much cleaner and visually appealing. Let's just try out the ovoid here. This is one of my favorite forms to play with the vector field. I find it just looks really neat how the shapes form upwards. So there is one situation where the conformal wavy field doesn't work very well, and that is when you have flat surfaces in the XY plane, which you can see with a cylinder. So when you look on the sides of the cylinder, you can see that it's behaving quite well, but when you look at the top here, it's quite unpredictable what happens with the conformal field on there. So I wanted to show you here the other option. This is less conformal because it radiates through all space, not necessarily just adhering to a particular surface. But I've added in here this radial vector field. So let's just plug that in, and you can see how that looks much better. Now it looks awful on the sides there because this radial field here is only along the XY plane. If we look at it this way, there's no there's no variation in the z, in either positive or negative z direction. So, but it does look really cool when you're just doing surfaces, because you can have the growth patterns, or in this case the orthoform lattice, sort of radiating out from a center point. So as I mentioned earlier, one of the main reasons that I've spent a lot of time figuring out complex vector fields is because I use them for growth algorithms. So let's first of all, let's get rid of that orthoform there, and we will go to our ovoid shape here. So I've already run a bunch of growth algorithms on this shape. So these forms that I'm about to show you aren't being formed right now, but I've imported them from earlier. So this one right here is one of my favorites, and just let me erase that there. And I've also got a funny plane in there. I'll erase that. So this right here is a growth algorithm that starts with seed points at the bottom, 12 in this case, and the points are translated a specified distance, and they're translated along the vector field. So you can see why it's important to have a nice clean vector field for this, if you want your growth to grow along the surface of your form. This particular algorithm, when the distance between 2 points gets large enough, it splits, and when the distance gets small, it converges again back into line. So that's one that I use quite often. But just to show you some other fun ones, I call this the worm vector field, because it starts the growth with a single point in the middle, and then it grows in the positive vector direction and a negative vector direction. So this right here is with no randomness to the vector field. Here's a little bit of randomness, and then this growth pattern here introduced quite a bit of randomness. Similar to that is this is a non-branching growth pattern. So it starts again with seed points, and in this case, when the lines get far enough apart, it starts another line in the middle, and then when the lines get close enough at a point, then the line stops, and the neighboring lines continue. And if you add a little bit of randomness into that vector field, it gets a lot more fun, these curvy lines. But again, no branching. Another algorithm is just this divergent branching vector field. So you can see that this the growth happens, and again it splits when the distance gets large enough. It splits and splits, but there's no function in here for it to converge or join up again. So when you have a situation where multiple lines are converging, they just kind of get crowded up there. And but you do get some interesting effects. So this is the same thing with a little bit of randomness introduced, and you can see the lines are just sort of clustering up there. And I'm showing you this in the conformal vector field just to give a contrast. This is the situation where I would actually use the radial vector field and make a divergent field right there. So this is the same branching growth pattern along a radial vector field. Really neat for making bowls and things like that. And then going back to the vector field that I started with there, or sorry, the growth algorithm that I started. This one diverges and converges. In this iteration here, it's just growing on a straight vector field, and then that's the same growth pattern applied to a more random vector field. So there's some of the fun things that you can do with these vector fields. And like I said, the growth algorithms are more complicated, a lot more fun, but I will hopefully do another or probably multiple tutorials on those at a later point. But there you have it, a little introduction to conformal vector fields, what they are and why they're important and fun to work with. And the test shape custom block, I'll give you access to the conformal, these two vector field custom blocks, and then the visualize vector field block here as well, just to use in your work. So thank you for joining in. I hope you hope you enjoyed, and tune in for the next one. Have fun making stuff.